Hello everyone, I'm Noor Safa and today I'll present the paper Graph Neural Networks Are More Powerful Than We Think by Kanatsoulis and Ribeiro. So to understand this paper, I'll go first over the research problem, the motivation, the proposed approach, the theoretical result, the architecture, and the experimental results. So, message passing GNNs are widely used for graph classification and node tasks. From prior theory, we know that their expressivity is upper bounded by one Wessler-Lehman test, or WL. This means if one WL fails to distinguish two non-isomorphic graphs, then a standard message passing GNN will also fail. So we can ask this question. If we have two non-isomorphic graphs with no informative node features, can a permutation equivariant GNN distinguish them? The classical answer is no, but this paper suggests that the answer depends on how we analyze the network. So, the key observation is that previous WL-based analysis assumed that the GNN starts with identical nodes feature, typically the all ones vector. This mirrors the initial coloring step in one WL. But from a spectral perspective, something interesting happens. The agency matrix can be decomposed as S equals U lambda U transpose, meaning filtering operates in the eigenvector basis. So if the input is all ones vector, then any eigenvector orthogonal to that vector contributes nothing to the output. So the entire spectral components vanish, and structural information encoded in those eigenvectors could be suppressed. So the author argues that the WL limitation arises from this input assumption, not from the message passing itself. So the natural question becomes, what happens if we change the input? To test this idea, the authors replaced the constant input with white random noise. So the input now has zero mean and identity covariance. They apply a standard polynomial graph filter, z equal the sum over k of h sub k s to the power kx. Instead of analyzing the mean output, which collapses under constant input, they analyze the variance. And here's the interesting point. The variance becomes a linear combination of the diagonal of s to the k. Now the diagonal of s to the k counts the number of closed walks of length k at each node. So the GNN is effectively extracting structural closed walk information that was previously invisible. This shows additional graph structure beyond what 1WL captures. This leads to the main theoretical results. If two non-isomorphic graphs have different eigenvalues, then there exists a message passing GNN that produces different equivariant outputs for them. Why is this significant? Because most real graphs have different eigenvalues, so this condition is not restrictive in practice. Therefore, the classical 1WL bound is not tight. And importantly, this stronger expressivity is achieved without higher order tensors, without symmetry breaking, and without modifying the message passing framework. The theoretical insight also translates into a practical architecture. The first layer computes closed walk features, effectively a deterministic version of the variance analysis. After that, the network continues as a standard message passing GNN, and permutation equivariance is preserved, computational cost remains comparable, and the model integrates naturally with existing GNN frameworks. To validate the theory, the authors evaluate the model on the CSL dataset, which is specifically designed to defeat 1WL. So, a standard GIN with constant input achieves random accuracy around 10%, but with the proposed modification, accuracy reaches 100%. On other benchmarks like EMDB, Reddit, Proteins, and Mutag, performance is comparable or maybe like slightly improved relative to GIN. So the theoretical gain is not just formal, but it produces measurable improvements, especially on WL pathological datasets. To conclude, the limitation of message passing GNN doesn't really come from the architecture itself, but it comes from the assumption that all nodes start with identical features. So when we look at the model from a spectral perspective and analyze variance instead of just the mean, we see that it can actually capture more structure than previously thought. The only remaining limitation is with co-spectral graphs. So the bottleneck wasn't message passing, it was how we were analyzing it. I'm leaving you with the references. Thank you.